A true aperiodic tiling stretches outward infinitely. Every local cluster of shapes is dictated by rigid geometric rules, yet the complete pattern never repeats. For decades, the standard way to quantify the data inside these infinite networks was to ask a strict combinatorial question. How many distinct colors are required to ensure that no two adjacent tiles share the same label? A proper graph coloring ensures local contrast across every edge. It solves the immediate adjacency conflict, but it treats each tile as an isolated unit, leaving the global rules that govern the pattern sequence unobserved. Mathematical analysis now requires deeper probes. For instance, with Markov partitions, a color assigned to a region acts as an algorithmic generator, predicting the exact geometric orientation of the tiles above it. Alternatively, Bake, Gaylor, Mazach, and Mitchell treat color as a physical scattering weight. By assigning numerical values to specific points in the tiling, they calculate the exact pure point diffraction spectrum of the entire structure. The question of how many colors has been outgrown. The modern imperative is to treat color strictly as a finite observable, deliberately deployed to probe an infinite system. To measure an infinite system accurately, we must observe the entire tiling hull. This animated diagram illustrates the hull, dynamically defined as the closure of its translation orbit. A central patch remains perfectly static, while the surrounding environment shifts to cycle through all legally permitted variations containing that center. This local consistency requires finite local complexity. Measuring any fixed radius across the plane, you will only ever encounter a finite number of distinct local patch types up to translation. Finite local complexity is the strict condition required for local derivations to function. Without it, encodings break down into infinite variables. A valid, finite observable must engage with the hull under these conditions without masking its global non-periodicity. If the observation is too coarse or the labels are poorly chosen, the measurement can hide the very aperiodic order it is meant to reveal. We can map out how different finite observables extract this data by moving through 5 specific regimes. Regime 1 is proper graph coloring. Mathematicians like Evans, Gowlack, and their colleagues compute exact optimal vertex and edge colorings for complex tilings. The specific invariant observed in this regime is local adjacency. The coloring algorithm isolates the exact chromatic numbers needed to satisfy the border constraints of the tiling skeleton. The cost of that exactness is scope. Chromatic numbers alone discard the deeper dynamical sequences and spectral frequencies of the hull. To capture that structural depth, we move to regime 2. Decorative matching rule coloring. This diagram demonstrates Goodman-Strauss decorations. Internal edge arrows are rigid rules, locking only where colors and directions align to form a larger supertile. As scale expands, these matching rules force a global substitution hierarchy across the plane. Here, colors act as witnesses of hierarchical membership. The difference between the first 2 regimes is exact. Proper graph coloring resolves a local border conflict. Matching rule decoration dictates which local patches are permitted to participate in a global substitution structure. Regime 3 is Wang edge coloring. We abandon polygons, morphing into rigid squares. Internal arrows become solid color bands, acting as absolute edge matching rules. If an adjacent edge color mismatches, the connection is mathematically rejected. This defines a 2-dimensional subshift of finite type. The edge colors themselves now function as the computational law defining global admissibility. They dictate the sequence of the subshift. This regime prioritizes pure computability. Geometric shape and its metric realization are intentionally abstracted away. Wang edge coloring proves that the structural rules of aperiodicity can be cleanly encoded into a finite alphabet, existing independent of any physical shape. Returning to the original polygonal geometry allows us to apply regime 4, Markov partition coding. This maps a precise triangular grid over a multicolored domain. The Lebesgue and Selinger construction directly links physical hat orientations to the underlying color regions. In a Markov partition, these finite labels code the long-term orbits of the dynamical system. Tracing an itinerary through this exact colored partition algorithmically generates valid infinite hat tilings. The invariant observed here is organizational. The color scheme provides a symbolic coordinate system for the geometric hull. While matching rules mechanically force a geometry to assemble, a Markov partition classifies it. It translates a continuous tiling hull into a discrete sequence of symbolic dynamics. The final perspective, Regime 5, abandons combinatorics and symbolic dynamics to observe spectral weighting. Here, we assign real or complex mathematical scattering strengths directly to specific control points on the geometric tiles. This sequence maps the transition from physical to spectral space. By tracking these weighted points, physicists compute the exact diffraction measure for monotiles, isolating sharp Bragg peaks. Alter the numerical weights, and the peaks shift, merge, or suppress in response. Changing these spectral weights probes the long-range order of the hull. It allows researchers to distinguish a true pure-point structure from homometric ambiguities, systems that look structurally identical but scatter light differently. Spectral weighting observes the ultimate physical signature of the infinite hull. It trades local patch constraints for the exact mathematical measurement of a tiling's diffraction. The current frontier in aperiodic research is mapping the relations between these regimes. We require a commutative comparison diagram that maps all 5 encodings: graph adjacencies, hierarchical arrows, Wang squares, Markov partitions, and diffraction peaks against the exact same aperiodic hull. The defining structural question is how these models relate. Are these distinct mathematical observables, mutually locally derivable, or are they factor maps? A mutually locally derivable relation is a lossless two-way translation. It means 2 different observables perfectly repackage the same aperiodic order. A factor map is a finite to 1 compression. It means one observable accurately sees a shadow of the system, but vital structural information has been permanently forgotten. This forces specific problems. For the specter monotile, do the algorithmic Markov partitions share the exact check cohomology as the mechanical matching rules? Does translating a geometry into Wang squares yield the same physical diffraction profile for natural weights? The lack of calibration across these models leads to a loss of fidelity. Different finite measurements can agree on local patches while providing contradictory data on the global spectrum or the system's topology. By defining color strictly as a controlled, mathematical, finite observable, discrete geometry moves definitively beyond asking how many colors. It begins interrogating the central tension of aperiodic dynamics. What exact portion of the infinite does the finite label actually know?